This is lecture 7a on examples of integration by parts. Let's write first the expression for integration by parts. So we will have some integral of u, what we're going to call dv, equals u times v minus the integral of v du. Instead of continuing to wax poetic about what this means, let's just do some examples. Okay, here is an integral, x e to the x. Now substitution is not going to work, and we're going to use integration by parts. So what we have to do is identify x e to the x dx in terms of a u and a dv. And there's two ways to do it. I'm going to just showing you some examples, and then you'll kind of pick up on this. Let's say that u is x. So I say the x is the u. Then I'm going to say that e to the x dx is my dv term. So the second part here, I identified, pen doesn't want to write, as dv. Right. Now if I look on this side, I will need the following. I will need v, I already have u, and I need a du. I'm sorry, yeah, that's what I'll need on this side. So I'm going to construct them. So first I identify. I say u is equal to x and dv is e to the x dx. Okay, now I must find u and du and v. So if u is x, du is dx. That's the same as you've always done with substitution. Now look at this. If dv is e to the x dx, then I must integrate and find out what v is. Obviously, v is e to the x. So this is what I do. This first line here is just an identification from the integral that you're given. And the next line that I've written here is a calculation. You differentiate u and get this term du. You integrate dv and you get the v. Now you assemble the right-hand side over here. So u dv equals u times v. So u is x, all right, put that right there. V is e to the x, there we go. That first term is taken care of. Minus, and now I'm integrating v, which is e to the x, times du. But du is dx. All right, you see, so we started with something that was seemingly impossible to solve, and we end up with an integral we can solve, and then we have another term out in front, the uv term out in front. Right. All of this constitutes the solution for this side. We no longer try to evaluate this side anymore. We just give it the answer that we obtained on the right-hand side. So I have x e to the x, of course that remains. Then I have to integrate the integral of e to the x dx, which is easy to integrate, minus e to the x plus some constant of integration. That is the answer. So your integral of x, I don't know why this pen doesn't write, e to the x dx is equal to x e to the x minus e to the x plus some constant of integration c. That's the answer. We don't go back and try to work on the left-hand side anymore. We have now solved it. This is our solution. Right. Now I said earlier that you have to make this identification. What term is u, what term is dv, and you can make it different ways. Some ways makes life easier. This was easy. This was correct. It was easy. Now, you can do it another way, and things will just get more and more complicated. That will let you know pretty fast that you're going in the wrong direction. So I'll show you that here. This is the other choice that we won't like. Let's say I have that integral, and I decide that u is e to the x. And dv is x dx. I can arrange it like that. That'd be perfectly fine. I could say it's e to the x, and then x dx. So I'm saying this is my u, I'm saying this is my dv, and we'll see where that gets us. So that was the identification line. just going to put that in blue. So here's the identification line that I chose. Now I have to do this calculation. So u e to the x, I can take the derivative here, and I have du equals e to the x dx. Fine, that's easy. Now, on this side, I have dv equals x dx. If I integrate this, I'll use the power rule and say that v is x squared over 2. Okay. Now, with these choices and all these terms either identified or calculated, I go back and reassemble my answer. So I'm reassembling this side, or I'm assembling this side. So u is e to the x, that's right here. V is x squared over 2, so I have that term, and the first term's taken care of. That's the easy part. Now it's minus this integral of v du. All right, so I have a 1/2, I'll put that out in front, and I'm integrating x squared e to the x dx. And now do I have something more complicated than I even started with? There's no problem, don't despair here. All you do is say, I'm going to go back and make different choices for u and v, and then for u and dv, and then it will be easy. Often, sometimes not, but that's the first thing you would do, is say, well, I've made something more complicated than I started with. Let me go back and make a different set of choices. And that's what you would go back and make this set of choices here. You just lose a little bit of time. It's not a big deal. Let's do some more examples. Here's another example that doesn't look like it should be integration by parts, but actually it is. I'm going to take the integral of the natural log of x dx. I'm going to use integration by parts. So I have to identify a u and a dv. So I'll say that u is the natural log of x, and dv is dx. All right? So now I take the derivative and end up with du as 1 over x dx by taking the derivative of natural log of x, which is 1 over x. Now I integrate this side. If dv is dx, then v is equal to x. And I'm going to take all that information, all those different functions, and I'm going to assemble the right-hand side here. So the integral of natural log of x dx equals, so I have a u, here's u, I put it second, but that's okay. So this is the u term, and this is the v term. All right, that's the easy part, of course, minus the integral of v du. Well, what is v? v is x, all right, and du is 1 over x dx. Well, the x's cancel, and all I'm integrating is the integral of dx. By the power rule, that gives me x, and there's my answer. The integral of natural log of x is x times the natural log of x minus x plus c. That seems unusual, not unexpected, because natural log of x is, well, it's a transcendental function. You can think that, well, there should be some easy solution for that. But instead, we had to use integration by parts to integrate the natural log of x. I think that's a homework or test question. Here's another example. Let's integrate x. So we're integrating x times the secant squared of x. Right. And we're going to integrate it by parts. So we have to choose a u and a dv. Let's say u is equal to x. And remember the rule of thumb, choose u so that's easy to differentiate and you don't end up with very many terms. If u is equal to x, du is dx. Well, that's pretty simple right there. Now look on the other side. If we say dv is secant squared of x dx, that's easy to integrate because the integral of secant squared is tangent. Now I have all the terms that I need. So I substitute that into this form. The first term is u times v. u is x. V is tangent of x, and that's the first term right here. Then I have this integral, the integral of v du. V is tangent of x, dx is du is dx. Right. Now here's my first term right here, and the integral of tangent x dx is the natural log of the absolute value of secant. I'm calling you that information right now. I'm just going to use that information just to continue on. In Calculus 2, unless it says explicitly that you must derive something, you can use the table of integrals, because that's definitely what you're going to do when you get out on your own. So here you have to learn various techniques. Now, integration by parts is something that you have to learn. but sometimes you can just use results in the back. So the whole idea here that I wanted to point out with this is how to choose the u and the v. U is something simple to differentiate. dv is something easy to integrate. You might recall from earlier work about L'Hopital's rule that with L'Hopital's rule, sometimes you had to use it repeatedly to get to the answer. Remember, you have an indeterminate form, you use L'Hopital's rule, you get another indeterminate form, you have to keep applying it over and over. Perhaps you recall that from first semester. For integration by parts, sometimes you have to also use it repetitively. This makes for a lot of terms in a list. It's important to keep your notation straight and give yourself lots of room to do the problem when this happens. So I'm going to demonstrate that with the integral of e to the x times the cosine of x dx. So first I have to integrate by parts, and this is my first pin. So here's my first integration by parts right here. So I'm going to make some choices. I'll let u be the cosine of x because that's easy enough to differentiate. I get du is minus sine x dx. All right. Then I'll say dv is e to the x dx, and let me integrate that and get v equals e to the x. Actually, you might say this is not going to simplify things. Truly, it is not, but you could choose in the other direction, you'll end up the same way. This is an example of where it will come out all right in the end. So let's go ahead and finish this first integration by parts. So e to the x cosine x dx, that's what I have here, and I'm breaking this up, so remember what I'm doing. It's the integral of u dv must equal u times v minus the integral of v du. So here was my u, here's the v. I wrote it in this order. It's a better order to write it in. And then it was minus, but I have a negative sign here, so I used a plus sign here, integrating e to the x sine x dx. Well, that's no simpler than what I started with. But in this case, you apply integration by parts again. And that's acceptable. Okay, in this case, I'll use the same sort of choices again. Let u be the sine of x, and dv equals e to the x dx. If I integrate sine x, I get cosine. All right, so that's taken care of here. Now differentiate. If I integrate e to the x dx, I get e to the x. Now let's put everything back together again. So what I'm really working on is just this rule right here. I'm just expanding this. So I'm using integration by parts on the leftover integral on the right-hand side. So what do I have here? When I'm integrating my original function, I have my original uv, which is right here. Let me get this highlighter so you can see the different terms. So I have this term, which persists here. Fine. And now I've taken this integral and I've integrated by parts. So there is a uv associated with it, which is e to the x times the sine of x. So that's right here, minus the integral of the of v du right here. So I started with, let me get this one in green. I start with this green one, and I end up with u times v minus the integral of v du. But I have to take the integral of v du and expand it by integration by parts. And here you can see it. All right, now, look at this. This is a special case. You see, here I end up with minus e to the x cosine x dx. Let me get the pen. See this term? And note its similarity to the term on the other side. Okay, so I can combine them. I'm going to add integral e to the x cosine x dx to both sides of the equation. I end up with a 2 over here. So I have 2 times my original green integral. That was supposed to be green. All right, but now there's a 2 multiplying it. I have the terms on the other side. I can isolate it by dividing by 1/2, and that's my answer. So, in other words, what this demonstrated was how to choose u and v, again, that you integrate by parts, but on the right-hand side, once you've integrated by parts, you have a term u times v here. Okay, well, somehow it draws. All right, and then I have this term. We're going to see if a mouse will work better than the pen. Perhaps it does. All right. But this integral in red sometimes requires integration by parts again. There's a homework or a test question where you do something similar to what is shown right here. And it has this nice result that once you integrate by parts again, you again get an integral that's the same on both sides. You can combine them, and then by dividing by 2, you get the answer. So here's the answer right here. The integral of e to the x cosine x dx equals 1/2 times the quantity e to the x cosine x plus e to the x sine x plus the constant of integration. Another use of integration by parts is to create what is called a reduction formula. Reduction formula applies to some usually transcendental function that's raised to a power n. For example, cosine raised to the power n of x dx. And we can integrate this by parts, and we end up with, I'm going to skip to the punchline here, we end up with the integral raised to a lower power, cosine raised to the n minus 2. We could apply this again. Gradually, we will decrease this by powers of 2 to where we get to an integral that we can evaluate, so it's just the cosine of x. So this is called a reduction formula. So what you did is started with cosine raised to some power n, and by applying integration by parts, you end up with another function. You end up with an expression involving another integral, but in this integral, cosine is raised to a smaller power. Right. And I'll quickly go through this. Again, we're using integration by parts, so I have to pick a u and a dv. So let's say u is cosine to the n minus 1, and dv is just the cosine of x dx. So I isolated one of the cosines over here. We'll see this again in, when we integrate functions, trigonometric functions. All right. Taking the derivative here, you see I have a loss of power by the chain rule. Now cosine is raised to the n minus 2. And now you see where the n minus 2 came from, because I isolated one of the cosine terms here in the u. The other one is over in the dv term. Integrating the dv side, I end up with v equals sine x. And now I can use this very famous Pythagorean Theorem, which should be embedded in your mind, of course, for trig functions, that sine squared plus cosine squared equals 1. All right. Now, what I have here will be sine squared. You see, when I assemble this integral, I'm going to have u v times du. So I have a sine here, a sine here. They're multiplied together, giving me the sine squared. But I can replace the sine squared with 1 minus cosine squared. All right. Then I multiply through, and then I multiply through, collect terms. Then I find that I can move one term over to the other side again. See, this one is the same here as it is over here. This is entirely messy, and I know it, and it's hard to follow here. But I combine those, and I get n raised to the cosine of n x dx equals cosine to the n minus 1 of x times sine of x. That doesn't need any integration. Plus n minus 1 times this integral of cosine raised to a smaller power. I divide by 1 over n, and that gives me that step, and that's the reduction formula. And here's the reduction formula. I divided by n, so I have cosine to the n minus 1 of x times the sine of x divided by n. That's my uv term. And then I have another integral of cosine, but raised to a smaller power. If I started with 4, now cosine would be squared. Right? If I started with 6, cosine would be to the 4th. Then I can apply the reduction formula again, and every time I apply it, I'm reducing the power of cosine. There's similar reduction formulas for sine, and there's actually several of them. You can see them in those table of integrals in the back of Stewart, also in Thomas too. And here's one for sine. Sine raised to the nth power here. By applying the reduction formula, I now have an integral involving sine raised to the n minus 2nd power.